All right. So on today's show, we get to begin, having started looking at right triangles, we get to look at a word you have probably heard about before. We're going to look at trigonometry. We're going to take a look at what it is, at why it works, and at how to use it to find one side of a right triangle. That's the idea. We want to use trigonometry today to find the length of a side of a right triangle. So how does all of this work? How does all of it play together? I will give you a right triangle. This is a right triangle. Could be any right triangle of any size. Let's call it triangle ABC, where C is the right angle. And what I'd like to do is I'd like to drop some perpendiculars. Perpendicular line, perpendicular line, perpendicular line. Maybe D, E, F, G, H, I. What do you notice about triangle HIA, triangle FGA, triangle DEA, and triangle BCA, the big one? Well, I noticed that those triangles are all the same shape, but they appear to be different sizes. One is a magnification of any other. And that almost makes sense. Why? Because all of those triangles share angle A, and all of those angles are right triangles. So by angle-angle similarity, all four triangles are similar to each other. What does that mean? That means that there are some ratios that hold. For example, the ratio of BC to AC, the vertical looking segment to the horizontal looking segment, is the same as a vertical looking segment to its corresponding horizontal segment, is the same as FG to AG, is the same as HI to AI. Vertical segment to horizontal segment is always the same all the way across the board. Similarly, we have two other sets of ratios we can say. We can compare all the vertical segments, BC, DE, FG, and HI. We could compare all of those to hypotenuses, BA, DA, FA, and HA. Those ratios will be the same because corresponding sides of similar triangles are in proportion. For that matter, we can take those four and compare them with bottoms. AC, AE, AG, and AI. Because in any triangle, in all of those triangles, the ratio of the horizontal segments to the hypotenuse is going to be the same. So here's where we make the jump. Because those ratios are always the same, and they all depend on angle A, we give them names. We call this ratio at the top, the ratio of the vertical to the horizontal, we call it the tangent of angle A. And we write tan A to mean the tangent of angle A. Similarly, the vertical as it compares to the hypotenuse. That is called the sine of A. It's called the sine of A, and we write that S-I-N. And this ratio here, the ratio of the horizontal to the hypotenuse, is called the cosine of angle A. And we write COS for cosine. But the big thing to know is that trig ratios work because similar triangles work. Similar triangles have sides that are in proportion. That's a big deal, which means that when I look at this right triangle with this angle A, C is the right angle, the lengths of the sides are little a, little b, and little c, and we name those because little a is opposite capital A, and little b is opposite capital B, and little c is opposite capital C. We can always know how to express the sine of A, and the cosine of A, and the tangent of A. And we do that by recognizing that the sine of angle A, by definition, is A over C. The sine of angle A is the opposite side over the hypotenuse. So if I'm looking at angle A, little a is the opposite side. Angle C, side C is the hypotenuse. Well, what about B? Well, B is the leg that snuggles up to angle A, and so B is what we call the adjacent side. And by definition, the cosine of angle A is the adjacent over the hypotenuse. Cosine is adjacent over hypotenuse. And then tangent is A over B. Tangent is the opposite side over the adjacent side. And so math teachers over the years have come up with some interesting mnemonic devices, interesting ways to help people remember sine, cosine, and tangent. And the most common one by far is called SOHCAHTOA. SOHCAHTOA stands for sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. Oddly enough, armed with that knowledge, we can do just about any right triangle trig problem. Consider the following. I've got a right triangle. That's a 33-degree angle. That's an 8. That's an x. I want to find x. Since I have a right triangle, trigonometry is a possibility. If I'm given an angle, then trigonometry is a certainty. This is not a Pythagorean theorem problem because we do not have all three sides involved. Let's name everybody. With respect to this angle, the opposite side is over here. The hypotenuse is the biggest side, and the adjacent side is the leftover. It's the leg that snuggles up to the acute angle. So I have in my problem adjacent and hypotenuse. So I go back to my SOHCAHTOA and I look for adjacent and hypotenuse, and that tells me that I am about to solve this using cosine. Cosine of what? We always write cosine of an angle. Cosine of 33 degrees. And the cosine of 33 degrees is equal to adjacent over hypotenuse, x over 8. So I want to get x by itself. How do we do that? Well, roughly, we cross multiply. 8 times the cosine of 33 degrees is x. Well, now I need my calculator, which I happen to have handy. And my calculator says, oh, let's go into degree mode. I'm going to hit the mode button. There it is, mode button. I'm going to make sure that I am in degree mode because my angle is measured in degrees. What's a radian? You'll learn someday, I promise. How do I do this? 8 times the cosine of 33. There it is. And I write that down to whatever I was told to write that down to. Let's say we were supposed to write it to the nearest hundredth. If we were supposed to write it to the nearest hundredth, then x is 6.71. And you can find any side of any right triangle if you know one acute angle and one other side. So what if the picture looks like this? And there's a 68-degree angle up there, and that's an x, and that's a 6, and I want to know what x is. So how does this go? Well, let's name everybody. With respect to this acute angle, the opposite side is over here. The hypotenuse is the biggest side, and the adjacent side is the leg that snuggles up close to that acute angle. So I have in my problem opposite and adjacent. And if I have opposite and adjacent, I look to see opposite and adjacent. That is a tangent problem. Tangent of what? Well, the tangent of 68 degrees. Now, is it 6 over x, or is it x over 6? Well, I've got to go opposite over adjacent. That's 6 over x. So I want to know what x is, so we roughly cross multiply. X times the tangent of 68 degrees is equal to 6, and then we'll divide. So x is 6 divided by tangent 68. Now that's not bad, because I can go to my calculator and I can say 6 divided by the tangent of 68, and I have an answer. I have an answer. I type it in just like so. And let's pretend we were told to round it to the nearest tenth. We write 2.4, and we put a nice pretty box around it. All right? I'll do one more with you. I'll do one more. We'll find one more side. I've got myself a 36-degree angle. That's a 10. That's an x. I'm looking for, here we go, the big guy's the hypotenuse. With respect to that acute angle, the opposite side is all the way over there. The adjacent side is the one that snuggles up alongside the 36. So in our problem, we have opposite and hypotenuse. So I go to my mnemonic device, and I'm looking for opposite and hypotenuse. That's a sine problem. Sine of what? Sine of 36 degrees. Is it x over 10 or 10 over x? Well, in this case, it is 10 over x, because we're looking for sine that's opposite over hypotenuse. Well, I'll cross multiply. X times the sine of 36 is equal to 10. So x is 10 divided by the sine of 36. So take a moment to plug that into your machine. And lo and behold, let's pretend that we were asked to find that to the nearest whole number. Oh, let's pretend we were asked to find that to the nearest tenth. To the nearest tenth, you still have to write the 0. To the nearest tenth, that's 17.0. You have to write the tenths place down. Okay, so it's a quick introduction. And I promise in our next lesson we will stick with these ideas and we will use them to find angles instead of sides. And then we'll take a day and we'll put it all together with some application. But here's the big thing for you to remember. Trigonometry works exactly because similar triangles work. Trigonometry works because similar triangles work, and so we get the ratios to work out all the time. All right, I'll go one more.